Oh, XO. Oh, I haven't seen all this O, XO, and for a while.
That's the old Enigma coding stuff I was talking about now.
Oh, really?
Hope they find fun, but old-fashioned. Right. Now, why isn't it showing different whiteboards? Oh,
Can you see, John? Can you see on the top left there is a arrow to the left?
yeah, I'm pressing that. Nothing is happening.
I
Oh,
think. Do you have two screens or one screen?
I've just got the one screen at the moment.
So
Show. Oh, no. Oh, let's close and start again. Share application. Whiteboard is up and running. I'm in Google. Application window. Share.
Share screen instead of share application.
Ah, there. Yeah, great. Don't know what happened last time. Now, what was the date last week? It was the 26th, I think.
Yeah, it's already. No, it's 19th, I think.
Yeah.
Last week was 26th. Yeah.
Yeah, this is the one.
Okay.
Oh, soon I've got to the end of it. All right. My screen pen. Hi. Can everybody hear and see me?
Yes.
Fantastic. Right, like Tatiana, I'm coming to the end of the new material I want to expose you to. We've got a session today which I'm going to look at texture recognition. Some of it is new ideas. Others will be using work we've covered before, such as the distance classifier. Next week, I would like to finish on new material, and I'd like to give you an insight into image retrieval. It's something you do all the time with your Google and whatever. You go searching images and you search content or search similar images based solely on the content, the visual content of the images. The big question is, how is this done and how good is it? So I want to talk a little bit about that. Then afterwards, I think there's 3 weeks left. I will come online at the timetabled time and we'll go over questions or any points that you would like to do. If you can give me a view of what you want me to talk about beforehand, then that might be useful. So after next week, we will basically be in revision mode and seminar mode. Right, today, texture recognition. Let's get my... In the past 2 or 3 weeks, we've been looking at window operators, starting from the very simple single pixel operators, which can change contrast and brightness. That's quite useful because it leads to image enhancement. We've looked at filtering, high pass and low pass filtering, which changes the quality of the images. And we've also looked at edge detection, which is a 2-window operator. And if you're looking at or done any reading or looking at images that have been edged, you will find that the quality is not particularly good, because what we are picking out is intensity changes, rapid changes from black and white or color, dark to light colors in an image, which the algorithms perceive as an edge, but we don't. And I'm just looking outside my window now, and I'm looking around, and I see a gravel path. I see a big Leylandii tree. I see grass. I see the sky and clouds. And these are the sort of patterns I want to start thinking about. How can we recognize those? And they contain texture. And the problem with texture is it's homogeneous across a particular shape. I'm looking at the trees and the leaves are all the same, but one can't focus and extract precise features the same as you might extract the letter T from a piece of text. So the texture recognition problem is a problem which is, it occurs throughout the textures, and somehow we are trying to extract information which is unique to that texture. And the question is, how do we do it? Well, the first approach would be frequency analysis. And if you have a search around, you will, don't you change again? What did I touch, Tatiana? Now she's gone. Oh, let's start again. 1, frequency analysis. And there are 2D Fourier transforms. And you can apply these to images, and it will give you the spectrum of the frequency content. And a 2D Fourier transform is a transform. It actually creates another picture which can be displayed as an image. And at the center is the DC. So we have a center point, which is the DC. And the DC in terms of images is the area of constant intensity or constant color. And from the outside, we get increasing frequencies. And as we rotate around, we get points which have a phase angle. So this would be a phase angle. Now, relax, Fourier analysis won't be in the exam. It is a complicated process. It is very time consuming. And if you're applying it to 16 megapixel images, even with modern computing, there is an awful lot of processing that we have to do. And you end up with a picture, and the picture looks a bit like a starburst. And it's a difficult medium to recognize. Humans looking at Fourier transforms are less able to make decisions than they can on the original image. So we're going to look at new methods for texture recognition, and these are going to be based on window operations. Whoops, what's happened there? So it really follows on from the edge detection and all the other window-based operators we've been looking at recently. Right. You cannot detect textures with single pixel operators. I'll try and get my writing a little bit better. Common sense. If I take a single, let's take a texture, for example. Let's take a high frequency texture. I'll use this example. And again, my examples will be very small, 4 by 4, just to give you a proof of concept. You've got to scale them up to real images to do some useful work. And if I took an image like this, and let's have a checkerboard. Let's have those two. Yes, that's it. I think everyone is alternating. Yeah, that's correct. And that is a high frequency image. And high frequency means lots of changes between pixels. And if I now take a second image, which is the same resolution 4x4 as an example, and let's take this. Same pixel density in terms of crosses and noughts and ones, and this would be a low frequency image. And if I were to take a single pixel operator, which would be sitting on a window space, a window pixel there or there, the single pixel binary images, 0 and 1. And one cannot tell whether it's from the high frequency image or the low frequency image. It's either a 0 or a 1. 0 could come from here, the 0 could come from there. The 1, it could be there, it could be there. So we don't have enough information on a single pixel to project texture. So texture is in fact a higher order property. In similar way to the Entipole system, the TY. It's similar to the Entipole system. If we take a single pixel, the decisions we can make are limited. For binary, it's 0 and 1. If I take 8 pixels, I can make 2 to the 8, 256 different decisions on the site. So we need an operator. And the operator I'm going to take is the simplest operator possible. It's going to be 2 pixels. Now, up till now, we've used these window operators, and we have had weights in them which determine how they behave. Texture recognition is different. The operator extracts information from the image. Rather than processing the image information. So if I were to take this operator and I was going to apply it to these 2 images, the operator now sitting, going back to the first image, in the first position, we would extract the value under the window, and let's put it in binary. It would be state 0, 1, assuming the cross is 1. If I move the operator to the next position, it would extract 1, 0. And if we let the operator scan the image, extracting the information at each point the operator can extract information from the image, we can get a histogram. Oh, go away. Oh, what's happened there? You don't want to do a Foundations of Engineering assignment, do you? Oh, goodness me. How did that happen? Can you still see me?
Yeah, we can still see you.
Right. Oh, damn it. I should have to.
Okay, now I can't see anything.
No, I've lost it now. Oh, technology. We need artificial intelligence. Oh, I've lost it completely now. What has happened to this stupid thing? Let's go back and set it up again. Hi guys, can you see me?
Hello, everyone. I noticed John has problem with connection. Please be with me. I'll try to resolve and find out what's going on. Hi, John. You were off. Can you hear me, John?
On. Can you hear me now? Get the bloody whiteboard up. Where are you, you damn thing?
John, the students can hear you now.
I know they can. Apologize for my language. Right, can you see me?
Yes, we can see your whiteboard and it's all good.
Thank God for that. Sorry about that, folks. Oh, now get into. I don't want tablet mode. Let's start again. We weren't on high pass filters. Will this scan up to where I was? Right, I'm soon. Oh, what's that? Ah, yes, here we are. Right, I'm back. I am back. Oh, okay, guys. Hope you're listening and seeing. We're looking at some very simple textures to try and develop a method for texture recognition. We have a 2-pixel window. There is the window. Let's call the contents A and B. The window scans a representative texture, and let's call this pattern A, which is a high frequency pattern. It's a checkerboard. And here we have a low frequency pattern, which is a vertical bar, basically half black and half white. The number of pixels set to 1 are the same, so the bit intensity of the two images are identical. Right. The operator scans the images. Let's try and get this a bit smaller so I can get it on the screen. And we obtain a histogram, good old-fashioned histogram. And the histogram, slightly different from the image histograms we've used before. It is going to be the number of states, number of occurrences. But instead of intensity as the horizontal axis, we are going to use the value of the state. I.e., what is the window looking at? And of course, a 2-bit window looking at a binary image, it can have 0, 0, it can have 0, 1, it can have 1, 0, and it can have 1, 1. No need to shout, it's not a K-map. So let's scan the image with the operator. And in the first position, the state is 0, 1. Move it over 1 pixel, we will have 1, 0, then 0, 1, new line, 1, 0, 0, 1, 1, 0. And briefly looking at that image, let's count up the number of 0, 1 states. It's going to be the position there, 0, 1, 2, 3, 4, 5, 6. There are going to be 6 occurrences in that image when we have 0, 1. Oh, 0, 0. There's none for 0, 0 on the histogram. So the 0, 1 is going to be 6. Let's draw that down there, and that is going to be 6. Now the number of occurrences of 1, 0, 1, 2, 3, 4, 5, 6 again. And there is no occurrences of 1, 1 in that image. Now, of course, what you would do is you would put the window in the first position and increment the entry on the histogram. I've looked at the image and looked for each individual state how many times they've occurred. Same idea. So we've got a histogram, and that histogram can lead or can be represented as a vector. And it's pattern A. Let's call it vector A. It's going to be a 4-dimensional vector. It is going to be the intensities of each state. Element 1 is 0, 0, element 2, 0, 1, and so on. So the vector is going to be, for this particular state, it is going to be 0, 6, 6, 0. And that will be the vector. Now let's take the second image for, this is histogram A. Let's have histogram B. And the same process for the second image. Let's draw the histogram. It is going to be 0, 0. Again, offset it from the vertical axis because you will have entries at the lowest point of the histogram. 0, 1, 1, 0, and 1, 1. And going back to the image, let's do the 4 states all at once. There's going to be 1, 2, 3, 4 positions where I'm going to get 0, 0. So the entry for 0, 0 is going to be 4. Let's label the axis. This is a number of states. And this is the value, same as before. Now back to the second pattern. The number of 0, 1s, well, I'm going to get 1, 2, 3, 4. 4 states or 4 entries at 0, 1. So I'm going to get 4 there. 1, 0, 0. No occurrence of 1, 0 when the window, the 2-pixel window, scans image B. And finally, 1, 1, you can see there's going to be 4 states. Which will give me a vector, a reference vector B for the B texture is going to be 4, 4, 0, 4. A different vector from the previous one. Now, having got those vectors, let's put in a test pattern. And the test pattern I want to put in and it is going to be this image. Four by 4 pixels, and I will have this pattern. Now, perceptually, I hope you would agree, if you had that as an unknown pattern, and these are reference patterns, I hope you would say the unknown pattern is more like B than it is A. So how can we actually classify that? Again, obtain the histogram. And the histogram in this case, again, number and value. It's going to be 0, 0, 0, 1, 1, 0, and 1, 1. And extracting the information clearly by inspection, there's going to be 1, 2, 3, 4, 5, 6 positions where we get 0, 0. No 0, 1s, no 1, 0s, but 1, 2, 3, 4, 5, 6 1, 1s. Which will give me a vector, let's call this pattern C. C is going to be equal to 6, 0, 0, 6. Right, so we've got vector 1, vector 2, unknown vector 3. We want to classify it. What technique do you know for classifying patterns in vector form? Well, the obvious one to go for is the distance classifier. And this will enable me to do a little bit of revision on the distance classifier, because if I have two patterns AB, DAB, a Euclidean, is equal to, I hope this is not new to you because we've covered it before, the summation I equals 1 to D of AI minus BI, all squared, which is a multi-dimensional version of Pythagoras' theorem. And of course, we have 4 dimensions in this problem. So using the distance classifier, DAB for these examples No, we don't want DAB. Those are the reference patterns. We want to classify C. So DAC, the distance of C from A, is going to be, there's vector C, there's vector A. Let's write it down, 0660. Well, you can see by inspection it's going to be 0. Because A was equal to 0660. And we are getting the distance. No, of course it's not going to be 0, silly me. It is going to be, let's write it down, 0 minus 6 squared plus 6 minus 0 squared plus 6 minus 0 squared plus 0 minus 6 squared. This is A1, this is A2, A3, A4, and the subtractee is the C's. And of course, the square root, tidy that up. They're all going to be 6s. It's going to be 6 squared in each term. 36, 72, 144. Square root of 144 is a distance of 12. So DAC is going to be 12. Let's now get DBC, the distance of C from reference B. And where was reference B? It was 4404. So B equals 4404, a vector, not a number, and C was equal to, was it 6000, 6006, I think it was. So those are the two patterns. Now getting the Euclidean distance for those, it is going to be, let's change color to make it the square root of B minus C. Let's do it in our heads. 4 minus 6 is going to be minus 2 squared plus 4 minus 0, which is going to be 4 squared, plus 0 minus 0 is going to be 0, forget about it, plus 4 minus 6 is minus 2 squared. And tidying that up, we've got 4, 16 is 20, and 4 is 24. So root 24. Is that correct? 4, 16, and 4 is 20, 24. And root 24 is damn near 5, isn't it? It's approximately equal to 4, let's say 4.8. So we've got a distance of 4.8 of C from B, and we've got a distance of 12 from C from A. According to the distance classifier, C belongs to B. Now go back to the images. Does that make sense? There was pattern C, and the classification is, it's one of those. So yes, I think that agrees with human perception. And while I'm talking of distance classifiers, they might come up in the exams. Let's remind you, it can use the approximate distance. And the approximate distance, there are two of them. There is the city block. The city block distance, DAC, is the summation I equals 1 to D, in our case 4 dimensions, of the mod of AI minus BI. Or you can use the square, and the square DAC is going to be equal to the maximum I equals 1 to D of the mod. I'll use one of them. I'll use the city block, see if we get the same decision. So the city block Let's write down the vectors again. They've gone off the screen. A, B, C. The C was 6, 0, 0, 6. B was 4, 4, 0, 4. And A was, what was it? 0, 6, 6, 0. Right, so using the city, don't you disappear! Oh, you sod! Excuse my language. Let's change color. DAC is going to be the summation of the difference between them. 0 minus 6 mod is going to be, let's write it down, 0 minus 6 mod plus 6 minus 0 mod plus 6 minus 0 mod plus 0 minus 6 mod. In fact, it's going to be 6, 12, 24. So the city block will give a distance of 24. Going back to D, B, C, the distance of C from the B reference. And that is going to be, we should be able to do it in our heads. BC is these two. The difference is going to be the mod of the difference. 4 minus 6 is 2, and 4 is 6, and 0 and 2 is 8. So the answer is 8. Now clearly 24, 8, minimum distance 8, B is C, which is the same as what we had with the Euclidean distance. So there's a bit of revision for you. Okay, so that's a concept. We have a problem, however, when we go to, oh, don't you disappear, when we go to real natural data. And the problem with natural data is if you threshold an image, to get binary, you would use an awful lot of information, huge information loss. Take a picture of grass or gravel and put a threshold of the pixels, a certain value, and see if you can retain the detail of the intensity. It will be lost. The picture will white out or black out. We need gray values or multi-level values. i.e. gray for black and white or color. Right, let's go to a window which is slightly bigger, which would be better for a real image. Let's take a 4-pixel operator. And let's take 4 pixels, vertical, horizontal. And let's call those pixel values A, B, C, and D. These are now real numbers. For real images, if it was gray, it would be between 0 to 255. Right, now if we're combining values, 256 values for each of those, there would be a huge number of combinations we could extract. And clearly that would be totally impractical. So we need to have a process which will generalize the overall shape of the texture. And this is known as the rank operator. Instead of working out all possible gray level states of the combinations, which in fact would be 255 to the power 4, or 256 to the power 4. Look at the relative values of A, B, C, D. And the relative values have a limited number of combinations. We could start off with a window position, looking at the underlying pixel values. We could find out that A is greater than or equal to B, is greater than equal to C, is greater than or equal to D. Now, if we look at the order of the pixels, choice of 4 pixels can be the brightest. That leaves 3 to be the next, 2 to be the next, and we've got no choice for the 4. The total number of combinations is 4 factorial. How am I doing for time? Gosh, I'm running out of time, damn it. The rank can range from that order to the exact opposite, which would be D is greater than C, is greater than B, is greater than A. And there will be 24 values. And if we encode the values 1 to 24, these will be the states on the histogram. And they can be the rank order. And what we're getting is generalization from the ranking, which reduces the number of combinations. For example, if I have 2 pixel sites where I've got A is 14, B is 12, C is 10, and D is 3. Now, clearly, those are low values. It's going to be a very dark sample, but the order is, amongst the dark sample, the A is the brightest and the D is the darkest. If I take another sample in the white region, 255, 200, 100, and 4, exactly the same rank. So the ranking would bring those two relative ranks together. A is greater than B, is greater than C, is greater than D. So we get insensitivity, we get elimination of the effect of brightness and even contrast. As long as the order is the same, the pixels are ranked with the same rank. So apply the ranking operation. This would give us 24 states. Now get the histogram. And the histogram now is going to be the ranks, number against rank. And the rank will go from, in this case, 1 to 24. How am I going for time? I'm running out of time. It would give you a 24 element vector histogram. So histogram to vector to distance classifier. And how well does it work? Well, you'll have to take my word for this because the results are in my office and I can't show you them. But we took a real world texture. This is a PhD project a few years ago. And the image was grass, a lawn. We extracted a window from that image and we rotated the window 90 degrees. So we just took it and we turned it round. So that became the top and those became the sides. The image looked almost like the original grass. It was apparent to the human a similar texture. But if you look very carefully, you could see a perceptual change between the rotated part and the normal part. Applied the texture recognition algorithm to it, and we were able to recognize those two as different regions. And it would do the separation. Now, that is a better result than you can ever achieve with frequency analysis, because the frequencies would be the same. And certainly edge detection would not go anywhere near it. So that was a preliminary research result, but it looked pretty good. So maybe this approach to texture recognition has some value. I've run out of time. I'm sorry about the mess up with the technology. I don't know what happened, but at least I hope you've got a new idea for texture recognition. Next week, I will look at image retrieval, as I said, and then we will go into revision mode. So once again, sorry about the loss of time. Have a good day and see you next week. Any questions? Anybody left? Okay, thanks, guys.